So in this video, I'm going to briefly introduce piecewise defined functions. And piecewise defined functions get sort of short shrift in this and other classes. I mean, looking ahead a little, we're introducing these so that we can do examples involving them in the continuity section. And after that, we'll basically never look at a piecewise defined function again. Um, which is a little unfortunate because I mean these things get used all the time and they're not some, arcane or mysterious concept. You know, piecewise defined functions get used when one function needs multiple equations to express it. And it's not hard to come up with examples of this from a wide variety of disciplines. So, in business, the classic functions are cost, revenue, profit. And let's let P of X be the profit from manufacturing X gadgets. You manufacture and sell them. But this is just the profit you get from creating gadgets. And, no real effort to make this realistic. But maybe you have a function like this. P of x is negative 0.05 x squared plus 100 x minus 200. If we look at the graph, well, it's a quadratic. Um, if you're not selling much, you're not making a profit. In fact, if you sell nothing, you're making a loss. The more you sell, the more profit you make, but that cannot go on forever. Eventually, limitations of the market and diseconomies of scale kick in, and your profit begins to decrease, even though you're selling more widgets. A pretty classic example. Now, let's take this example and modify it a little. Let's suppose this object that we are manufacturing is seasonal. We are manufacturing swimwear, for example. Well, is this profit function going to be the same in July as it is in December if we're manufacturing swimwear? Probably not, right? So it no longer makes sense to have a single profit function. Instead, we could think of having two profit functions. Behold, a piecewise defined function. Um, as I suggested earlier, piecewise defined functions show up all over the place. Let me give me a second. So, an example near and dear to my heart because I did my dissertation on this, looking at applications of differential equations and mathematics to biological systems. Suppose we're looking at the growth of yeast in a bioreactor. So the input is going to be the amount of time since the yeast cell came into being via cell division. The output is going to be the size of the cell. And I'm not worried about in fact, the equations are complicated. That was sort of the point of my research. So I'm not going to put explicit equations down for you. What I am going to say is that yeast can be both aerobic. Let me make sure I'm spelling these words right. Aerobic or it can be anaerobic. And what this means, I mean, this isn't going to be on a test or anything, but yeast can thrive in the presence of oxygen, or it can thrive in the absence of oxygen. And it's aerobic if there's plenty of oxygen. It's anaerobic if there isn't oxygen. And yeast grows in both these environments, but it doesn't grow at the same rate. So you need a piecewise defined function. Let's just make something up. You need one function if you're in an aerobic environment, and you need a different function if you're in an anaerobic environment. So again, a piecewise defined function. Now, the way these are here, whether this is in season or out of season, whether this is aerobic or anaerobic, that's not showing up explicitly in the equations, right? I mean, there's no in-season variable or out-of-season variable. There's no aerobic variable. There's no anaerobic variable. The piecewise defined functions we're going to look at in this class are going to look like this. You know, the exact function. These I just made up off the spur of the moment, but where x is, is going to control which piece we use. So a little different from my two introductory examples. So for example, let's say we have f of -3. Well, we go over here and we ask, where's this input? Where's -3? Well, it our options are that it's less than 0, that it's between 0 and 10, or that it's greater than 10. And of course, -3 is less than 0. So we use that first piece. F of 5. Well, now 5 is between 0 and 10. Now our input is here, so we use the second piece. And f of, let's make this less than or equal to f of 11. Well, 11 is greater than or equal to 10, so we're in this piece. And we'll see realistic examples of this in the exercises. Like, the tax rate depends on your income, but you're probably aware that there are different tax brackets. So your tax rate depends on your income, but what formula you use depends also on your income. So we'll see more real world examples of this, but here's just a quick introductory example.